Hello students, today we are going to discuss the introduction of the complex integration. So in this session we are not going to only discuss the theory, also side by side we are going to discuss some practical applications of the integrations, mainly the line integration and some solutions. Before I start the lecture, I want to say one thing: please do not skip the video, else you will not be able to understand the intermediate theory and the concepts, so it will not be beneficial for you. So if you want to know the subject, if you want to do the solutions in the exam, so please follow the entire video for your beneficial. So before we are going to start, first of all we are going to start with the different types of curves in the complex plane. So here we are focusing basically over the parametric curves in a complex plane. Parametric curves in a complex plane. So everyone know that any complex number that we can write down in the form of z equals to x plus iy, where x denotes the real part and I is the imaginary part. Now if we are considering that x equals to some function of t and y equals to some function of other function of t, say x equals to phi of t and y equals to psi of t, where we will assume that both x and y are continuous function of the real parameter t, where t is lying between some closed and bounded interval, and bounded interval a to b. A and b are the real numbers. So this is the representation of any complex number in the plane, Argand plane. So for example, here we are taken one very known curve in the Cartesian coordinate system, that is y square equals to 4ax. Everyone know that this is represents a parabola, right? So now if we take the parametric form of the parabola, that is x equals to at square and y equals to 2at. So the graph of the parabola that we have drawn here, this represents the real axis and this is the imaginary axis, because in the complex plane we should not write down x-axis and y-axis. That x-axis is considered as the real part, so it is along the real axis, and y is along the imaginary part. So if we plot this y square equals to 4x, so the parabola will be look like this, that everyone know. And if we take any particular point on the parabola, that is the z, so z will be given by this form, that is x plus iy. So x equals to at square and y equals to 2at. Now we are going to come discuss some different types of curves in the complex plane. So first we are coming to the first curve, that is known as the simple curve. So what is a simple curve? That is, suppose we are having a parametric form of a curve, that is zt equals to phi of t plus I psi of t. So this curve is said to be a simple curve if it does not intersect itself. Say this is our real axis and this is our imaginary axis. So here you can see one curve I have drawn here. So this curve is not intersecting itself. So if such curve exists which are not intersecting itself, it is said to be a simple curve. But if the curve is intersect itself somewhere intermediate point, so that curve is not considered as a simple curve. The next curve that we are going to discuss is the closed curve. A simple curve is said to be a closed curve if we can see the two of its endpoints basically coincide. So it is quite like a closed region, closed type of region which is enclosed by some curve. So you can imagine of a circle that is coinciding two endpoints. So here the diagram which is representing a closed curve. Now the next curve is very important curve, that is a smooth curve. So in the complex plane, some curves are said to be smooth curve if we can see that it possesses a unique tangent at each and every point on the curve. So from the calculus point of view, you know that to draw the tangent, unique tangent, basically the curve should be a differentiable curve, right? So we will be able to differentiate the curve, and the value of the differentiation at a particular point will be the unique value, right? Non-zero unique value. So a curve is said to be a smooth curve if it is a continuous curve, as well as it should be having non-zero derivative, differentiable. So this curve is said to be a just an example of a smooth curve. So at each and every point you will be able to draw one unique tangent, right? And everyone know what is a tangent. So that is a straight line which will touch the curve at some particular point, and it will basically one kind of say that differentiation, that each and every tangent if we draw, that means these points where we will be able to differentiate the curve. Next one, that is the most vital curve in the complex plane, that is known as the contour. So what is a contour? So basically contour is nothing but a kind of smooth curve, but not necessarily a full smooth curve. It can be a piecewise smooth curve. So little bit relaxation we have given to the smooth curve. So that kind of curve is said to be a contour. So it is not only a smooth curve, it can be a piecewise smooth curve also. So if you are imagine of a just a smooth curve, so that is also a contour. But if you are imagine of a piecewise smooth curve, that is also a contour. So we can say in this manner that every smooth curve can be a contour, but every contour not necessarily a smooth curve. It can be made of or consist of finite number of smooth curves. So for example, in this diagram you will see that I have drawn one triangle, right? So this triangle is a consist of three part, that is three straight lines, where each and of these straight lines are nothing but representing smooth curves. But the three vertices of this tangent, they are creating the pencil of the arc. So at the pencil of the arc, the unique tangent is not possible. We can draw infinite number of many tangents through this point, vertices, right? So this points, that is the vertices, are not the points where the function should be differentiable. So here this curve is not differentiable at these vertices, so we will not get unique tangent at these vertices. But except for these points, if we are imagine of this straight line, then along the straight line the tangent can be drawn at each and every point, and that will be a unique tangent. Okay, now similarly if we just go to this point, this is wholly a closed curve and it is a smooth curve, so it is possible to draw unique tangent at each and every point. So it is a contour, and this is also a contour. What is the difference between these two? It is a contour as well as a smooth curve, but it is a piecewise smooth curve, so it is only a contour, it cannot be a smooth curve, right? Now we come to some regions over the complex plane based on these concepts of this smooth curve and the closed curve, etc. So two kinds of region usually we get. First one is known as the simply connected region, and second one is the multiply connected region. So what is a simply connected region and what is multiply connected region? Let us try to understand. So suppose we are having an open region D. An open region D, it is said to be a simply connected region. That is, if every simple curve in D encloses only the points of D. Encloses only the points of D. What does it means? It means that suppose we are having an open region and we have drawn some simple closed curve on that region. Now if we want to shrink the curve, it will not leave the region. Okay, whatever we will shrink down, and after some certain time, if you understand that after some certain time, whenever we shrink the curve, it will just coincide to a point itself. So that point should be inside the domain, it should not be outside the domain. Okay, as well as we want to shrink it, it will not leave the domain or leave the region. So that kind of region is said to be the simply connected region. So here the diagram that is showing us the portion of a simply connected region. So in this region, if we draw any kind of curve, say any kind of simple curve, closed curve, if we want to draw, say I'm drawing one curve like this, another curve like this, I'm shrinking, right? So if I am shrinking this curve, so what will be the portion that we will what we can understand, that these curves are getting shrink down, but it is not leaving the whole region, right? So it is said to be a simply connected region. Now the regions which are not simply connected, it is said to be a multiply connected region. So for this example, I have given this curve. So here this annular portion which is shaded by the yellow color, so this portion is our region, but it is not a simply connected region, right? It is a multiply connected region. Why? Because suppose in this region I have made one curve. For your understanding, I am making one curve like this. Now if I want to shrink down the curve, after some time what will happen, whenever the lower line it will cross, it will come to another region. So it is leaving the region, it is not wholly inside this annular region. After some time, from this curve to this curve it will come, right? From this curve to this curve it will come. So it is not just wholly connected, we need that wholly just containing within that region. So this kind of region is said to be a multiply connected region. Now we come to the main topic of today's discussion, that is the complex integration. So here first of all, let us define the complex integration. Thereafter we will do some questions on it. So here for our basic understanding and easy way, we are considering a contour, that is a C be the contour, and we are considering another function fz, which is a continuous function and defined over the contour capital C. Now if we want to integrate f of z along the curve C, the integration is usually denoted by this one, that is integration over C f of z dz. Okay, so this is the line integration. Usually we will do it in the vector calculus also. The concepts of the vector calculus you can use here also. So integration over C f of z dz is represents the line integration, where C is the known as the path of the integration or the line of the integration. And usually whenever we are considering a closed curve, the integration takes the symbol like this, that is integration over the closed curve C. So within the integration, one circular motion you can see, so it is known as a circulation. Okay, so here we are considering integration over a closed contour C, and the motion of the direction of the curve is taken in the anti-clockwise sense. C is taken in the anti-clockwise direction. Now let us try to apply these concepts to do some questions of the line integration. So our first problem is that evaluate integration over the closed curve C, where the integration part is that dz upon z minus z0, and what is our closed curve, that is the z minus z0 equals to r. Okay, so first of all, whenever any kind of integration or line integration whenever you are having, you please try to identify what is your main function, right? What is your main function? So for this integration, our main function f of z, that you can imagine as f of z is nothing but 1 upon z minus z0. So 1 by z minus z0, this is our main function f of z. Now let us describe briefly about this curve C. What does this curve C represents to us? So this C, that is z minus z0 equals to r, it represents a circle which is centered at a point z0 and the radius of the circle is r. Always you have to remember this one whenever you are having this. Now the value of z0 sometime can be given 0 itself. So if it is 0, then you have to think it is a circle centered at a point 0 itself and the radius of the circle is r. Okay, so here for your understanding I have given one brief calculation about this circle. So say this is the real axis and imaginary axis. So z0 is the center and r is the radius. How we can get this? Because we know that every complex number can be put in the form z equals to x plus iy, right? And z0 equals to, say we are taking one point, arbitrary point on the complex plane, that is x0 plus iy0. Now mod of z minus z0 equals to r. In place of z and z0 we can substitute the points, and taking the whole square of the modulus, we are having mod x minus x0 whole square plus y minus y0 whole square equals to r square. So definitely all of you can be able to understand it is representing a circle which is centered at x0 comma y0, and the radius of the circle is r. Now the polar form of the circle that we know, that x equals to r cos theta and y equals to r sin theta, right? So to do such kind of integration, usually we convert the integration into the polar coordinate system. That will be easier to solve. So z minus z0 equals to r. So if we just remove the modulus, so that will represent any arbitrary point on this circle, on the circumference of the circle. So that can be given by z minus z0 equals to r e power I theta. This formula also you have to remember. How it is coming, if you want to know that, we can made it another video lecture, so there we will be able to discuss. But it is very simple to understand. Just you substitute x equals to r cos theta, y equal to r sin theta. You can get this form z minus z0 equals to r e power I theta from the equation of the circle. So z0 is the fixed point and z is our variable point, and theta is also varying, right? Now how theta will range for a circle? So theta will start from 0, and to get the whole circle we have to rotate the theta 360 degree, that is 0 to 2 pi. So theta will get the rotation for 0 to 2 pi, and z is the variable here. Now let us differentiate the z. So we will get dz equals to r e power I theta into I and d theta, right? Dz equals to this r I e power I theta d theta. Now this is our given integration, dz upon z minus z0. So here we will substitute the value of the curve. So curve is from theta equals to 0 to 2 pi, because we have taken one circle here. Now substituting the value of dz, that is r I e power I theta d theta, divided by z minus z0 is nothing but r e power I theta. So r e power I theta can be cancelled down from this portion to this portion. So you can see, so what will be left in the numerator? That is I only. So I d theta, 0 to 2 pi. I is constant of the integration, so it will come outside. Integration will be theta. So range from 0 to 2 pi, so it will simply come 2 pi I. It is very interesting and important integration. Later also we will be able to use the result of this integration directly. Okay, so wherever you will see this kind of value is there, that is dz upon z minus z0, where z0 is the interior point of the domain. The result of the integration is going to be 2 pi I only. Now let us come to the another form of the integration that is also interesting and quite complex. Many times we have seen that students make the mistake. They think that the first integration has been given and they will do the mistake here. So only one change I have done in this question. Now the problem is, that is dz upon z minus z0 whole to the power n, right? Z minus z0 whole to the power n. So for the previous question power was 1 only, but here it is given as power n, where n is a positive integer, not necessarily equals to 1. If it equals to 1, then it will become the previous question. So here we are considering n is a positive integer and n must be greater or equals to 2. So the same process of the integration, that is z minus z0 equals to r. So any point on the circle can be represented by z minus z0 equals to r I e power I theta, right? So now z equals to z0 will go in the right hand side. So z0 plus r I e power I theta. So from here we will get the differentiation part of the z, that is dz equals to r I e power I theta d theta. Now we are going to substitute every value in this integration. So integration over c dz upon z minus z0 whole to the power n. This is going to be 0 to 2 pi r I e power I theta divided by r to the power n e power I n theta. So here r is going to cancel, one r is going to cancel from here. So the denominator we are having r to the power n minus 1. This I is going to be outside, and we are having 0 to 2 pi e power I. If we take common, then 1 minus n theta, right? So now we have to integrate this. So whenever we will integrate this, what we will get from here, that is I divided by r to the power n minus 1, it is outside, e to the power I 1 minus n theta divided by I 1 minus n. Range of the integration is 0 to 2 pi. Now all of you know the Euler's formula. What is the Euler's formula? That is e power I theta can be written as cos theta plus I sin theta, right? So that is known as the Euler's formula. So using this Euler's formula, what we can write down, e power I 1 minus n theta as cos 1 minus n theta plus I sin 1 minus n theta over the limit 0 to 2 pi. Since n greater equals to 2, so whenever we will put cos of 1 minus n theta 2 pi, so it will become cos even pi, because 2 pi is there. So cos even pi is always equals to 1, okay, and cos 0 equals to 1. So here it is becoming 1 minus 1 0. So first term is going to vanish, right? The second term, sine of any kind of pi, that is sine integer, any integer into pi, n pi, sine n pi is going to be always 0. So 0 minus 0, it is equals to 0. So ultimately what is happening here, the whole numerator is going to be 0. So ultimately the answer is going to be 0 only. Okay, so only one changes we have done with the previous question, that is here the denominator we are making whole to the power n, where n is a positive integer greater equals to 2, so the result is going to be 0. But if n equals to 1, then dz upon z minus z0, this result is going to be 2 pi I for the same circle, that is z minus z0 equals to r. Over the same circle we are doing the integration. Now let us come to do some different type of integration where the curve is not necessarily a circle. So how we can proceed? So for an example, we have taken another integration. Evaluate integration 0 to 1 plus I z square dz along the curve y equals to x. So it is just a straight line, y equals to x. So for this curve y equals to x, if we draw the diagram, so this is our real axis, this is our imaginary axis, y equals to x, it is a straight line. Now 0 to 1 plus I, this is the limit of the integration, it is limit of z only. So z equals to 0 is our origin, and z equals to 1 plus I, basically the coefficients here we have to take of I, that is 1 comma 1. So z equals to 1 comma 1 is the another point. So in between z equal to 0 and z equal to 1, we have to join this line, right, through the line y equals to x, over which we have to integrate z square function. So our f of z is nothing but z square. So what is z in complex plane? X plus iy. So you can put z equals to x plus iy. In place of d of z, also you can put d of x plus iy. So now for this curve y equals to x, whenever I want to go along the curve, what is the value of y? The value of y is x. So everywhere wherever we will see y, in place of y we can substitute y equals to x itself. So this y is changes into x, this y also changes into x. So now it is just a simplification, that is a plus b whole square formula I have taken here, and here also 1 plus I is taken common, so it is becoming d of x only. Now everyone know that I square is equals to minus 1, because it is a imaginary number, I equals to root over of minus 1. So x square and this I x whole square, these two terms are basically getting cancelled out. okay, from from this first bracket part. So we are having with 2i(x) square along with 1 plus I is the constant. So you can take this 2i 1 plus I out of this integration, and here here basically that is a 2i 1 plus I you have to take common, and x square integration is x cube by 3. Limit of the integration becomes 0 to 1. Now one thing I forget to tell, that from 0 to 1 plus I, how it becomes 0 to 1, right? How it becomes 0 to 1. So here basically what I am doing, we are substituting y equals to x. So if we substitute y equals to x, so every terms in this integration is becomes depends on x only. And what is the limit of x for this line? 0 to 1, right? So that's why this limit changes from 0 to 1. Okay, so ultimately the answer is coming 2 into 1 plus I divided by 3. Very simple to implement. Let us come to the last problem of today's session. So here, for your understanding, better understanding, little bit more complex problem I have chosen, and here we are taking the parametric form of the curve. So suppose we want to evaluate the integration over C. The function f of z is taken as z bar. Okay, z bar, that is the conjugate of z, dz, where C is the portion of the parabola from the point 0, 0 to the point 1, 2, and x equals to t square and y equals to 2t. The form of the parametric form of the parabola is given here. So basically here the parabola is y square equals to 4x. No a is there, a equals to considered as 1. So the same thing, same procedure, that is we have to consider z equals to x plus iy. So if z equals to x plus iy, what is our z bar? Z bar is going to be x minus iy, that is a conjugate of z, and in place of x and y you can put x equal to t square and y equals to 2t. So it will become t square minus I 2t. Now let us differentiate z, because we need dz also in the integration. So what is dz? Dx plus I dy, right? So now x equal to t square, but we have to convert in terms of t everything. So x equal to t square means dx equals to 2t dt. Similarly y equals to 2t. So what is our dy? Dy will become 2 dt. So for the previous question, since y and x they are given as a relation, but here y and x relationship is not been given, the parametric form of the equation has been given. So everything we are changing in terms of the parameter, and the limit of the integration also will depends on the parameter. So now suppose if we want to just substitute everything, then what we will get from dz? Dz will become 2t dt plus I 2 dt. So 2t plus 2i dt. 2 plus 2i you can take, that is t will come outside. So here we are going to substitute. Now the parameter t is coming from 0 to 1. So let us explain how this parameter is going to be t equal to 0 to 1. So if you just notice, the integration goes from 0, 0 to 1, 2. So if you just look at any one of the variable, suppose x is ranges from 0 to 1. So x is ranges from 0 to 1. So what is our x value? X equals to t square, and we are considering only in the positive side, right? So if x equal to 0, then t is also equals to what? T is also equals to 0. And if x equals to 1, then using x equal to t square, what we will get? The value of t is also equal to 1. So t will ranges from 0 to 1. You can implement this idea for y also. Suppose if you take y limit, so y is going from 0 to 2, right? And y equals to given as y equal to 2t. Y equal to 2t. So if I substitute y equal to 2t, so 2t equal to 0 imply t equal to 0, and 2t equal to 2 imply t equal to 1. Anyhow, in any direction you will go, the same result for t you will receive, that is t equal to 0 to 1. So now it is a simple calculation. So after doing the calculation, we are having this value of the integration like this, that is a 2t cube plus I 4t square plus 2it square minus 4i square t. Is the simplification I have done because that you can practice from it, you can do by yourself, and you can check each and every step. So I am not making any kind of step jump so that it will be helpful for you. So the simple integration we have done, and the limit of t has been put 0 to 1, and the final answer is coming 5 by 2 minus 2 by 3 I. So with this today's lecture we are ending.